Calculate the magnitude and direction of the Coulomb force on each of the three charges shown in the figure. So as you can see, we have three charges, one blue charge and two orange charges. Let's call the blue charge Q1. Let's call the other two orange charges Q2 and Q3. I want to focus on just Q1 and I want to get the net force acting on Q1. I know that Q1 is going to be attracted to Q2. And so how do we illustrate that? We draw force vectors and we call this first vector F12 and this other vector F21. But we're only interested in F12 because it is the force acting on Q1 and we are only going to solve for Q1 for this example. You can do Q2 and Q3. Now we know that Q1 is attracted to Q2, but it is also attracted to Q3. I think at a lesser force because it's Q3 is far away. But we indicate that attraction with two force vectors F13 and F31. But we're not really interested in F31, we're interested only in F13 because we're focusing on getting the net force on Q1. So you can see now there are two forces acting on Q1. We have F12 and F13. So what we do know right now is that F12 has a north direction, but what is the direction of F13? If we have a protractor, we can obtain the direction. For example, here, with the help of a protractor, we find that this vector right here, it's different from F13, but we can see that this vector is 27 degrees north of east. That's one way of defining the direction of a force vector or a vector in general. You write the number of degrees and you write north of east if that degrees is measured north from east. Or you can also say the equivalent 60 degrees is of north. Or you can simply say 27 degrees. I think it's the most convenient, 27 degrees. But we don't have a protractor, so we can just use trigonometry to solve this problem. So again, our problem is how do we get the direction of F13? I'm going to draw F13 again. What we want to happen is we want to know this force F13. We want to know the direction of that force. And we want to be able to define this direction in terms of this angle here. We want to know that angle. And we don't have a protractor, so we just use trigonometry. We notice that the three charges form a right triangle to be. So that will really help us because, oh, it's missing, it's gone. Okay, that will really help us because this is what we do. Remember alternate interior angles theorem? What we want to do is we want to know what this angle is because that's just equivalent to this outer angle by virtue of the alternate interior angles theorem. So knowing this angle here inside the triangle is basically knowing what the angle for our direction for our force 13 is. Let's just bring this triangle to the upper right hand corner. And now we have this upper side which is adjacent to theta. That's our adjacent side, point 3, and this is our opposite side, point 1. So if you remember SOHCAHTOA, we know now that tangent theta is opposite over adjacent. The opposite side is point 1 meters and the adjacent side is point 3 meters. And if you convert that into arctangent, you will find theta. And that happens to be 18.4 degrees. So we now know that this angle inside the triangle, that it is 18.4 degrees, but according to alternate interior angles theorem, this angle outside the triangle is also 18.4 degrees. So the angle that F13 makes with the positive x-axis is 18.4 degrees. So what we do know now, we now know that for Q1, F12 is directed north and F13 is directed 18.4 degrees north of east. Pretty cool. We already know the directions, but we have to know the magnitudes as well. And that's the easy bit. The magnitude is just, we can obtain that using Coulomb's law. I want you to review that, and if you have any questions, just message me. That's F12 we found using Coulomb's law to be 1.349 times 10 to the negative 5 newtons. And now let's solve for F13. Now the tricky part about F13 is what distance do we use for R13? R13 is the distance between Q1 and Q3. And again, you have to use your geometry or trigonometry. This distance right here you can obtain using Pythagorean theorem. So that's what explains the square root here. 0.3 squared plus 0.1 squared. This is just from the Pythagorean theorem. And the final answer for F13, it's 1.618 times 10 to the negative 6 newtons. So now we know the magnitudes and the directions of both F12 and F13. We know that the magnitude of F12 is 1.349 times 10 to the negative 5 newtons. We know that the magnitude of F13 is 1.618 times 10 to the negative 6 newtons. We are now ready to add these forces vectorially. And graphically, what does it mean to be adding two vectors? This is what it means to be adding two vectors. This vertical force vector is just F12. And in order to add F13 to F12, we just connect that F13 vector to the head of the first vector, F12. And after connecting F12 and F13, we now trace this orange vector, which starts at the beginning of F12 and ends at the end of F13. This is your Fnet Q1. This is the sum of F12 and F13. So that's how you do it graphically. This day I am going to teach you the component method of getting Fnet Q1. I think it's easier, but it's less intuitive. And I'm pretty sure you already know about this as well from your previous lessons back in grade 8 or grade 9. This is what we do. This is called the component method of getting Fnet. We list down first of all the forces. Here on the first column you write the forces F12, F13, and at the bottom is Fnet, or the sum of F12 and F13. Next, for the second column, we write down the x components and the y components. Now for F12, the x component is 0 because if you observe F12, it doesn't have an x component. It's purely vertical. So whenever you have a vector that is purely vertical, then the x component of that vector is 0. and that whole vector is its own y component, 1.349. Now F13 doesn't belong to a purely horizontal or purely vertical force vector. It does have an x component and a y component. F13's x component is known as F13x and is the shadow of F13 along the x-axis. F13y on the other hand is this one right here, completing the right triangle, and is the shadow of F13 along the y-axis. What are some interesting relationships? We know that F13 obeys the Pythagorean theorem with its x and y components. That could be useful someday, but maybe not today. But if we know theta here, we can also use SOHCAHTOA to make some interesting relationships. Like if you want to know the value of f13x, just remember that cosine theta is adjacent over hypotenuse. So cosine theta is equal to f13x over f13. Therefore, f13x is equal to f13 times cosine theta. If we use sine theta is f13y. The sine is opposite over hypotenuse over f13, and therefore f13 is y is equal to f13 cosine theta. And that's exactly what we did here for the x component. F13 is 1.618 times 10 to the negative 6, and we multiplied it by the cosine theta, which is theta is 18.4 degrees. And we obtained this value for the x component, and we obtained this value for the y component. F net x is just the sum of all the x components, and F net y is just the sum of all y components. So 0 plus 1.535 times 10 to the negative 6 is just 1.535 times 10 to the negative 6. And 1.349 times 10 to the negative 5 plus 5.107 times 10 to the negative 7. That gives us 1.4 times 10 to the negative 5 F net y. So now we are asked to calculate the magnitude and direction. For the magnitude, you now have f net x and f net y, so you just get the Pythagorean theorem, use the Pythagorean theorem to solve for f net. For the direction, you can use this formula. Theta is tangent inverse of f net y over f net x. And actually, I just solved for that earlier and typed it here. And we find that f net magnitude is 1.408 times 10 to the negative 5 newtons, and the direction is 83.74 degrees north of east. That's a long process. Thank you for your patience.